All right, let's talk about the AQA A-Level Computer Science Skeleton program. Now, if you're tackling this, you know it's way more than just lines of code. It's a living, breathing simulation. Today, we're going to pull back the curtain and show you exactly how this digital ant colony ticks, from the inside out.
And that's really the big question here, isn't it? How can a bunch of simple rules, just written out in Python, create behavior that feels so alive, so dynamic, and honestly, kind of unpredictable?
So, for just a minute, let's forget that this is exam material. What we're looking at is a blueprint for an entire ecosystem. We're about to see how different classes and objects all work together to simulate the life, the struggles, and even the communication of a whole ant colony.
Okay, so here's our game plan. We'll start with the big picture, then we'll literally build the world from the ground up. After that, we'll meet the ants, figure out how they talk to each other, see how the simulation actually runs step by step, and finally, we'll look at how you get to control the whole thing.
So let's kick things off with that big picture. Our goal here is to totally demystify this program so you know exactly what makes it tick. By the time we're done, you won't just understand the code, you'll get the why behind the design choices.
Okay, let's dive in. Every simulation needs a world, a stage for the action to happen on. So, how is this one built? Well, it all kicks off with one masterclass.
Meet the simulation class. You should really think of this thing as the game master. It's the boss. It reads a list of settings, builds the entire grid, and then places all the starting pieces on the board: the nests, the food, and the very first ants. It's basically the conductor for this whole orchestra.
And these are all the dials and knobs the game master gets to turn at the very beginning. The simulation parameters list defines everything: how big the world is, how many nests get created, how much food they start with, and even the physics of their communication, like how strong a pheromone trail is and how quickly it fades away.
So if the simulation is the entire game board, then the cell, well, that's just one single square. It's the simplest, most basic building block of this whole world. Every single cell knows its own coordinates, its row and column, and most importantly, how much food is sitting on top of it. Everything in this simulation happens inside one of these cells.
Now, this next part is a really crucial detail you're going to want to lock in on. The grid looks two-dimensional, right? But the code does something clever. It actually stores it as one long, single, one-dimensional list. The __get_index function is the magic translator that takes a row-column coordinate and figures out the exact spot in that list. It's a super common technique, and understanding it is key to navigating this world.
So we've got our world, but, a world is pretty boring without anyone in it, so let's meet the cast of this digital drama: the ants themselves. And this is where the power of object-oriented programming really starts to shine.
Think of it like a family tree. Right at the very top, you've got the base ant class. This is the blueprint for every single ant in the simulation. It lays out the common ground. Every ant has its own unique ID, it keeps track of how old it is, and it always knows where its home nest is.
And here is a perfect example of specialization. From that one base ant class, we get two totally different types of ants. You've got the worker ant, which is the forager. Its whole job is to find food and bring it back. Then you have the queen ant, who is the heart of the nest. She never leaves, but her presence is what allows the colony to grow. Two totally different jobs, but they both inherit those core features of being an ant.
Okay, so the workers need to find food, but this world can be huge. How do they navigate efficiently? How do they tell each other where the good stuff is? Well, that brings us to what I think is the most elegant part of the whole simulation: the invisible language of the pheromone trail.
Yeah, just think of a pheromone object as a digital breadcrumb. When a worker ant finds food and starts heading back home, it drops one of these in the cell it's moving through. And the most important part of this breadcrumb is its _strength value, which basically tells other ants how loud or fresh the signal is.
But here's the brilliant part: these trails don't last forever, and that's key. This one little line of code is what drives the entire navigation system. With every single turn of the simulation, every pheromone's strength goes down a little. This decay is absolutely vital. It makes sure old, useless trails fade away, which naturally guides other ants towards the freshest, most direct paths to a food source.
So we've got the world, we've got the ants, we've got their communication system, but how does anything actually happen? Let's look at the engine room of the simulation, the advanced stage method. When you advance the simulation by one stage, it's not just one big messy event. It's a very precise, ordered sequence of events. First, all the pheromones in the entire world decay a little bit. Second,
every single ant gets to take its turn to move or grab food or drop it off. And third, after the ants are done, every nest gets to process its resources, eating food and maybe, if they're lucky, creating new ants.
You know, for all this complex behavior we see, an ant's decision-making is surprisingly simple. It really just boils down to a basic if-else statement. If an ant is carrying food, its goal is simple: get home and leave a trail for others. But if it's searching, it follows the strongest pheromone trail it can find. And if there are no trails nearby, it just wanders randomly. That's it. That simple logic makes this whole complex system work.
And the nests have their own logic too. They aren't just passive buildings. In every stage, they have to consume food based on how many ants they're supporting. If they've got plenty of food, they have a chance to reproduce and make new workers. But if the food runs out, the nest might be forced to cull some of its own ants just to survive. It's a constant, delicate balance of feast or famine.
Okay, so we've gone deep into the guts of this digital ecosystem. So finally, let's pull back out and look at how the main function gives you a simple control panel to actually watch and interact with this world you've set in motion. This is your window into the simulation. The code gives you a simple menu that lets you act like a researcher. You can get a high-level overview of everything, you can zoom in on a specific area, or you can even inspect one single cell to see exactly what's going on in there. And of course, you are in control of time. You can move forward one tick at a time or jump ahead to see what happens.
And that really brings us to the big takeaway here. If you look at any single piece of this code, none of it is that complicated on its own. But when you combine all these simple rules for ants, rules for pheromones, rules for nests, you get this incredibly complex, emergent behavior that you couldn't have predicted. That is the power of object-oriented design, and it's the real lesson of this whole program.
And that leaves us with one final thought. Now that you've seen the blueprint, you know the rules of this little world. So the real test is, could you change them? What would you change first? Would you add a new type of ant? Maybe introduce some predators? Make the pheromones last longer or shorter? That's where the real thinking and the real fun begins.